Patty's Calculus Videos, written and performed by me, Patty Leitner.
Part 2, Derivatives. Section 2.7, Tangent Lines, Derivatives, and Velocity.
Lesson 3, Instantaneous and Average Velocity. Part 1.
Okay, the next thing we're going to do is kind of change gears a little bit and talk about something that may at first seem unrelated to what we've done before. We are going to talk about velocity. Well, you might think, what does velocity have to do with these curves and tangent lines to these curves and slopes of tangent lines to these curves? But it turns out that there's a very intimate connection between the idea of velocity and the idea of slopes of tangent lines. Well, to understand that, let's go ahead and just discuss a hypothetical kind of example. Suppose we're in this situation. You decide to drive from Concord, California to LA, California, and you start out at noon. So that's the time that you depart from Concord. We're going to let S be the variable that designates the distance you've traveled after T hours. T is going to be the time elapsed in hours past noon. So you drive a certain distance S in a certain number of hours T past your starting time of noon. So we could really think of S, that's the distance that you've traveled, as some function, I'm going to call it F, of the time that is elapsed since noon. So as more time goes by, you've gone a different distance, and so your distance, and remember it's traditional to use S for distance, your distance S is equal to some function of time. Now we don't know specifically what function of time it's equal to, so we're leaving this in a sort of imaginary realm. So it's some function of time. And down here I've actually graphed S equals f of t. That's the black graph that's right here. You notice I have the time t on the horizontal axis, and I have the distance you've traveled S along the vertical axis. So this is your distance in miles, and this along this axis is your time in hours. I should have mentioned up here, this is the distance you've traveled in miles. So those are just the units that we're going to use. Well, let's suppose further that at 3 p.m. you've gone 220 miles. So you start driving at noon, you keep driving, and at 3 p.m. you notice that you're now 220 miles from your starting point of Concord. So you notice on my graph here, when t equals 3 hours past noon, I have an output, it's a little bit tiny here, of 220 miles is how far you've traveled on your trip. Another way of saying this would be that f of 3 is equal to 220. At time t equal 3, S is equal to 220. Okay, at 5 p.m., so 5 hours after you leave on your trip, you've gone a total of 360 miles. You can see that on the graph here. When t is equal to 5, we have an output of 360. Or another way of saying that is that f evaluated at 5 would be equal to 360. So when your time t is 5, your distance S is equal to 360. What I'd like us to do is answer this question. What's your average speed? And by speed we roughly mean velocity. Velocity really includes the idea of a direction, and speed is really technically it's the absolute value of your velocity. But we're going to try to find your average speed, really your average velocity is what I should technically say, between 3 p.m. and 5 p.m. Well, this is a problem that we did way back in algebra classes. If I want your average, and I'll abbreviate it this way, velocity, remember that it's just the change in your distance over the change in your time. So I'm going to write it's the change, using my delta symbol, in your distance over the change in your time. Or if you want to use letters instead, you could say it's the change in S. S is the letter we're designating for your distance traveled, over the change in T. And T represents how many hours have gone by, your time. Okay, well, how do I figure that out? Well, I really want to just go ahead and think it's the difference in my distances over the difference in my times. It's really the distance at 5 hours minus the distance I've gone at 3 hours over the difference in my time, 5 hours minus 3 hours. Let's go ahead and write that out. We know what those distances are in this case because we're told right up here. F of 5, my distance after 5 hours, we said is 360 miles. So it's 360 miles minus F of 3, that's how far I've gone after 3 hours. We were told that was 220 miles. And I divide by my times, it's 5 hours minus 3 hours. Well, if we go ahead and compute this, 360 minus 220, that would be 140 miles in the numerator, and I'm dividing that by 5 hours minus 3 hours would be 2 hours in the denominator. I guess we could go ahead and reduce that. 140 over 2 would be 70 miles per hour. And with miles per hour, we often write it this way, 70 mph, which really means miles over hours or miles per hour. So your average speed between 3 p.m. and 5 p.m. on this driving trip is 70 miles per hour. What I'd like us to do next is to think about how that relates to our graph. We've just found actually a slope of something because we've found a difference in your S values, your distances, over a difference in your T values, your times. So this is actually, the 70 miles per hour is the slope of a line. And which line is it the slope of? So I'm going to say it's the slope of a certain line. And which line is it the slope of? Well, let's go up to my graph. It's really the slope of the line between the point P here and the point Q. It's the point corresponding to T equals 3 and the point corresponding to T equals 5. So if I were to draw a straight line through those 2 points, you might notice that my delta T is really the change in the times. That turned out to be 2 hours. That's really this distance along the T axis, 5 minus 3. And my delta S, that's what was in the numerator of our calculation, is really the change in my distances. That was the 360 minus 220. That turned out to be 140 miles. And if I do delta S over delta T, that's really the rise over the run of this green line. And what is that green line? It is actually a secant line to our curve. So this is a secant line. And it's the secant line through the point P and the point Q on our S equals F of T curve that we were originally given. So more specifically, it's the slope of the secant line through the points corresponding to, I'll abbreviate corresponding here, corresponding to T equals 3 and T equals 5. Okay, let's go ahead and look at the next page, and we're going to extend this imaginary trip to ask another question. So if you look at the next page, I have a kind of interesting question here. I'm going to be asking you this. Suppose you're at the 3 p.m. point on your trip. So you leave at noon from Concord, you're driving towards LA, maybe along Highway 5, you're driving. At 3 p.m., you look in your rearview mirror and you see the highway patrol behind you. I want to ask you the following question. Does that highway patrolman care about your average velocity? For example, if he notices that you're going 90 miles an hour or something like that, can you go ahead and say, oh, well, I was planning on reducing my speed over the next hour to something below the speed limit so that my average velocity over, say, a 2 or 3 hour time span would end up being something that is 65 miles per hour or under, and I can avoid getting a ticket. Well, unfortunately, highway patrolmen, I know from personal experience, do not care about your average velocity or that you were planning to drive slower later in your trip so that you end up with an average velocity that meets the speed limit. What they care about is what's called your instantaneous velocity. So I'm going to just put down here, no, he cares about how fast you're going at the instant that he is measuring your speed, maybe using his radar gun. He cares about what is referred to as your instantaneous velocity. It's how fast you're going at the moment that he spots you. It's really how fast you're going right at 3 p.m. He sees you, you're going 90 miles per hour. That's all he cares about, and he's going to write up his ticket accordingly. Well, the question becomes, how do we get from your average velocity to your instantaneous velocity? And let's think about a few different graphs here, and we'll try to understand how we could get from the way that we used to figure out velocities in algebra, doing the change in distance over the change in time, and ending up with an average velocity, to something that would be your velocity at an instant in time, right at 3 p.m., not from 3 p.m. to 5 p.m., but right at that moment, how fast you're going is really what your speedometer is showing you when you glance down at it at 3 p.m. Well, here's the picture that we talked about before. This is really the graph from the last page, where you're going from point P at 3 hours past noon to point Q at 5 hours past noon. And you might remember that we did the calculations there, and we said that your average velocity was just the change in the distance, which was 140 miles, over the change in the time. It was a 2-hour time span, and we ended up getting 70 miles per hour. And it was the slope of this secant line between the point P and the point Q. So it was just your delta S, the change in your distance, over your delta T, the change in your time, over that 2-hour time period. So notice that this is the average velocity over a 2-hour time period. Well, let's go ahead and try to get closer to the idea of an instantaneous velocity. 2-hour time period is a long time. Let's make it a 1-hour time period. So that's what we're going to do next, is leave P where it is at 3 p.m., but I'm going to choose a Q that corresponds to a T value of 4. So I'm going to figure out my average velocity from 3 p.m. to just 4 p.m. And if you thought about the secant line that goes through these 2 points, it would have some change in time. In fact, I can see that the change in time in this case will just be 1 hour. And there will be some change in the distance. And of course, we have to know how far you've gone at 4 p.m. And so that would have to be given to us because we don't know what function f of t is. If we were given the function, we could compute it. And I think I wrote down here that you've gone 310 miles at 4 p.m. and remember that you have gone 220 miles at 3 p.m. So if I want to figure out the average velocity, I do it exactly the way that I did before, and the average velocity would be the change in the distance. Well, that's 310 minus 220. 310 minus 220, that would give me 90. So the change in the distance, what goes in the numerator here, is 90 miles. And the change in the time, well, it's just a 1 hour time span, so just 1 hour. So we would have 90 miles per hour, or we usually write that as 90 mph, meaning 90 miles per hour. So now what we found is that between 3 and 4 p.m. your average velocity was actually even faster. Between 3 and 5 you're sort of slowing down, so your average velocity was a little bit slower, 70 miles per hour, but during this time span between 3 p.m. and 4 p.m. you were actually going pretty fast. You were going 90 miles per hour. Well, a 1 hour time span is not an instantaneous velocity. It's how fast we were going on average between 3 p.m. and 4 p.m. How can we get even closer to the idea of an instantaneous velocity? Well, we can do that by shrinking this time period. Instead of going 3 p.m. to 4 p.m., let's go say 3 p.m. to 3:30 p.m. And you could think of creating a new Q on your graph and a new secant line through those 2 points. And now we will have a new change in time. Our new change in time, delta t, it's even hard to write in there because our change in time is getting rather small, is really a half hour. It's 30 minutes, but in units of hours it would be 1/2 hour. And our change in distance, well, we don't really know that unless I tell you where you are on your trip, how many miles you've traveled at 3:30. And at 3:30 p.m., we're going to assume that you are at mile number 270 on your trip. And remember, at 3 p.m., you're at 220 miles from Concord. That's how far you've gone. So if I want your average velocity over that half-hour time period, I would evaluate it the same way. The average velocity would be the change in s over the change in t. The change in s now, let's see, 270 minus 220 would give me 50. So the change in my distance is 50 miles. And I divide by the change in the time, which is 1/2 hour. If I invert and multiply, it would be 50 times 2 over 1, and that would still be miles over hours. And that would end up being 100 miles per hour. So this is looking even a little bit worse. Between 3 and 3:30 p.m., your average velocity was even faster. It was 100 miles per hour. Well, a half-hour period is fairly short, but it's nowhere near an instantaneous velocity. Let's get closer to your instantaneous velocity by shrinking this time difference, this time span, even more. Instead of going from 3 to 3:30, I'm going to go from 3 p.m., and it's hard to draw on here because it's so close, but I'm going to go to 3:01 p.m. In other words, we are going to have a time difference of 1 minute, and that's a very short time span in terms of driving. So the new Q that I get is even closer to my P. I draw the secant line through those 2 points, and I find that average velocity. Well, the change in the time is right here. I can't even squeeze it in, it's so small. The change in the time is 1 minute, but we'd like to write that in terms of hours since we're working in units of hours here, 1 minute is a 60th of an hour, so it's a very small fraction of an hour. And the change in the distance, well, again, I would have to tell you, since we aren't given a formula for the function f of t, I would have to tell you how far you've gone after 1 minute at 3:01 in the afternoon. And I'm going to put down that you are at mile 222 at 3:01. And remember that at 3 p.m. you were at mile 220. So the change in your distance is going to be 222 miles minus 220 miles. That equals 2 miles. So if I want your average velocity over that very small time span of 1 minute, your average velocity, well, that would be the change in your distance, that's just 2 miles, over the change in your time, that's 1/60th of an hour. If I invert and multiply the 1/60th, I get 2 times 60 over 1. That's still in units of miles per hour. And 2 times 60, that's 120 miles per hour, mph. So, yikes, this is pretty close to your instantaneous velocity. It's your velocity over a 1 minute time span, and unfortunately, you were going an average of 120 miles per hour over that 1 minute time span. That's pretty close, probably, to what the Highway Patrol measured as your instantaneous velocity at 3 p.m. But here's the question that I want us to think about. What would have to happen to get your instantaneous velocity? We got something that we think is probably pretty close to your instantaneous velocity, but it's really still an average velocity. What would have to happen to get your true instantaneous velocity instead of this average velocity over some definite time span? Well, our time span, our delta t, the period over which we're figuring out our average velocity, would need to get even smaller. In fact, our delta t, the change in our time, would have to shrink all the way to 0 to get the true instantaneous velocity. If we could keep doing this, maybe go from 3 p.m. to 3 p.m. plus 1 second instead of 1 minute, we would get even closer to our instantaneous velocity. But if we could somehow allow delta t to shrink all the way to 0, then we would get our true instantaneous velocity. Well, let's think about it for a moment in terms of the graph. As delta t shrinks to 0, what's going to happen to this point Q that we've got here? Here we had P is fixed, but here we had Q when we had a 2-hour time span was up here. When we had a 1-hour time span, notice Q has moved closer along the curve towards the point P. When we had a half-hour time span, Q was even closer to P. And when we had a 1 minute time span, Q was very, very close to P, even closer than I was able to draw it here because of the thickness of my pen. So notice that as delta t goes towards 0, I'll say i.e., according to the graph, Q is approaching P on the graph. Now, each time we figured out your average velocity, we were really figuring out the slope of a secant line on the graph. Here's our first secant line, here's our second secant line, here's our third secant line, and here's our last secant line. It's really a sequence of secant lines as Q gets closer and closer to P. And what happens as our point Q slides down towards P? What happens to our secant lines? We said that our secant lines are getting closer and closer to the tangent line, just as we talked about at the beginning of this section. It's a sequence of secant lines, and as that delta t shrinks down to 0, it's the same as we had an x down here before, but now it's a t value. It's the same as t going closer and closer to our a value of 3 here. And so our secant lines are actually getting closer and closer to the tangent line. In the limit, when delta t shrinks all the way to 0 and this t value goes all the way to 3, we would end up with q being right on top of our p, and we would end up with the tangent line to this distance versus time curve at the point corresponding to exactly 3 p.m. So in the limit, we would actually get a tangent line here. And remember that the slope of the secant line was our average velocity. And so if we allowed our time scale, delta t, our time span, to shrink to 0, allow q to slide down the curve towards p, allow the secant lines to get closer and closer to the tangent line, it must mean that the slopes of the secant lines are getting closer and closer to the slope of the tangent line. And so the slope of this tangent line must be the instantaneous velocity that we are going. So we shrink delta t down to being 0 in size. We go from the secant lines to a tangent line. The slopes of the secant lines are getting closer and closer to the slope of the tangent line, and thus the slope of the tangent line must be exactly equal to what we were hunting for, which was the instantaneous velocity rather than the average velocity. That is the velocity that the highway patrolman is interested in. And if we knew the function s equals f of t, we could actually find that instantaneous velocity by finding the slope of the tangent line at the point corresponding to t equals 3. So in this picture, I'm just going to jot down again for us, t has shrunk all the way down to 0, and we are really finding the slope of the tangent line and instantaneous velocity. And it turns out, I know this sort of magically in my head because I have a certain function f of t in mind, that the instantaneous velocity turns out to be 123 miles per hour, which is pretty close to what we estimated when we found the average velocity over that tiny time span of just 1 minute, 1/60th of an hour. But the instantaneous velocity, unfortunately, is even a little bit higher than that. The instantaneous velocity that the highway patrolman measured at the moment 3 p.m. when he's behind you, clocking you, is 123 miles per hour, and you're going to get a big fat ticket. Okay, let's go ahead and go to the next page, and we'll summarize some of these ideas that we talked about in this kind of imaginary thought example. So let's go to this page where we'll summarize your average velocity, how we find that, as compared to your instantaneous velocity and how we find that. So the average velocity, remember we said graphically, that's the slope of the secant line that goes through the 2 points corresponding to the times that you're finding the average velocity over, 3 p.m. to 5 p.m. in our very first example. So the average velocity is found simply by finding the slope of the secant line. And to figure out the slope of any line, remember you just do the rise over the run. When it's an s versus t curve, that would be the change in your distance over the change in time. And if you're given a specific function s equals some specific formula f of t, then you can find the change in the distance simply by plugging in your end time. We're ending at 5 p.m., so you find f of 5, subtracting your the function evaluated at your beginning time, f of 3, and then dividing by the change in the time, 5 minus 3. So finding your average velocity is really just finding the difference in the outputs and dividing by the difference in the input values. And graphically, it's the slope of this secant line through 2 points. finding your instantaneous velocity, we said graphically is the same as finding the slope of the tangent line instead of the slope of the secant line. It's essentially the line that you get by shrinking this time difference down to 0, choosing an ending time that's closer and closer to 3. And in the limit, when your delta t shrinks all the way to 0, you will end up with your instantaneous velocity. So the instantaneous velocity is the slope of this tangent line. And how do we find the slope of a tangent line? Well, that's what we discussed in the whole first portion of this lesson. The slope of the tangent line, if we know the curve is s equals f of t, the slope of the tangent line at p to this curve, f of t, is simply the derivative of f of t. It's f prime of t. And we would just evaluate that at t equal 3, so this would be at a general time t. But if I want the instantaneous velocity at 3 p.m., I would just find f prime and evaluate it at 3. So I would find f prime evaluated at t equal 3. And how do I find f prime of t, or in particular f prime of 3? Well, we just use our limit formula. We would do the limit as h approaches 0 of, and in general it would be f of t plus h. If I want it right at t equal 3, it would be f of 3 plus h minus, in general it's f of t, but if I want it right at 3 p.m., it would be f of 3, and we divide the whole thing by h. Usually we'll find the derivative for general value t, and then we'll find the instantaneous velocity by plugging in the specific time at which we want our velocity, 3 p.m. in this particular case. Okay, so that's how we find the velocity at a time 3, the instantaneous velocity. We find the derivative and plug in 3. If in a slightly more general setting I want to find the instantaneous velocity at time t equals a, I would do exactly the same thing. So the instantaneous velocity at t equals a would just be equal to f prime evaluated at a, where f is our position function, so s is equal to f of t. And because this comes up so often in these distance versus time types of applications, we actually give the instantaneous velocity function its own name, and we use the letter v for the instantaneous velocity. In this case, it would be the instantaneous velocity at the time t equals a. So if s equals f of t is the position function, or it's sometimes called the distance function, it's how far we've moved in t hours or t minutes, whatever units we're working with, v is equal to the derivative of that, so the instantaneous velocity is f prime of t. Okay, well, let's write this down in general. If I want then the instantaneous velocity, we're calling that v of a, that's the instantaneous velocity at time t equals a. That's the same thing as my position function's derivative evaluated at a, f prime of a. And of course we could write out what f prime of a is. That's the limit as h approaches 0 of, and instead of f of 3 plus h minus f of 3, we will now have f of a plus h minus f of a, all divided by h. And remember that geometrically, this is just the slope of the tangent line at the t value t equals a on our s equals f of t, on our position graph, our s versus t function. So the number that we end up getting for this limit which is the instantaneous velocity of our car or whatever object we're looking at that's moving, is really the slope of this tangent line right at the point P that corresponds to a t value of a.